Every advanced chip in your phone, your car, or your data center traces back to one company on one island. TSMC produces roughly 90% of the world's leading-edge semiconductors. There is no second source, no meaningful backup, and replicating this capacity would take years, even under ideal conditions. The question isn't whether this bottleneck matters, it's how an entire global economy came to rest on a single point of failure. According to the TSMC 2024 Business Overview, published in April 2024, this single manufacturer produces roughly 90% of the world's leading-edge semiconductors, the newest, highest performance chips in existence. A separate measure reveals an even broader footprint. In the wider pure-play foundry market, TrendForce's fourth quarter 2025 analysis shows that TSMC captures 70% of all global revenue. These percentages measure entirely different denominators. Together, they outline a stark reality. A highly concentrated hub in Taiwan fulfills the processing demands of the entire modern world. The question remains how this extreme concentration formed. In 1987, Morris Chang, a veteran executive who spent 25 years rising through the ranks of Texas Instruments, proposed a radical restructuring of the global technology market. At the time, the semiconductor industry relied on integrated device manufacturers, single entities that both designed and fabricated their own silicon. Chang's venture, the Taiwan Semiconductor Manufacturing Company, broke this combined structure by establishing a pure-play foundry. In plain terms, a foundry physically manufactures chips but designs none of them. This allowed the rise of fabless companies, designers like NVIDIA, Apple, and Qualcomm, that create complex architectures but outsource the physical fabrication. To de-risk this model, Chang secured critical initial backing. Taiwan's government and the Industrial Technology Research Institute provided seed capital and research support, while Dutch electronics giant Philips contributed technology and equity. Public stock listings in the 1990s supplied capital for physical expansion, enabling TSMC to lead the industry-wide shift toward larger 300mm wafers. Because TSMC promised never to compete with its own clients, it secured institutional trust. This neutrality triggered a self-reinforcing feedback loop. As more designers chose the platform, production volume grew. This volume generated the enormous capital reserves and specialized engineering expertise required to fund next-generation process development, drawing a highly concentrated network of suppliers directly to the island. According to a profile published by the Institute of Electrical and Electronics Engineers, Chang recognized that by consolidating global demand, a pure-play foundry could achieve scale advantages that no single integrated competitor could match. This structural loop turned a neutral manufacturing service into an indispensable global utility, leaving a stark economic dilemma. Once the industry perfected this centralized platform, how does anyone begin to replace it? Replicating this infrastructure requires crossing a financial threshold that rises with every technological shift. TrendForce and EE Times market analyses estimate that building a single, state-of-the-art semiconductor fab now requires between $20 and $35 billion. This capital must be spent before the first commercial wafer is printed. The investment does not fund a typical factory, but a sealed environment where clean rooms, chemical handling, and water systems operate as a single organism. Inside, specialized tools like extreme ultraviolet lithography systems, each costing upwards of $200 million, must project light with atomic precision. Yet, constructing the shell and installing the machinery is merely the physical baseline. A completed building is not a functioning fab. The true barrier is achieving repeatable production at scale, calibrating highly sensitive systems to yield flawless silicon day after day. This mechanical calibration relies on decades of unwritten operational knowledge. Inside Taiwan's established semiconductor clusters, engineers transfer specialized process adjustments from one generation of fabs to the next, continuously optimizing yield. The precise percentage of working chips produced per silicon wafer. This human expertise is supported by a dense, hyper-local supplier network. Because component manufacturers, equipment specialists, and chemical suppliers operate within minutes of the main clean rooms, a new Taiwanese fab can reach commercial production in roughly 2 years. When these projects move overseas, the timeline fractures. In Arizona, Japan, and Germany, comparable facility projects can take nearly twice as long to construct and cost approximately twice as much. These stark variations depend on localized labor markets, regulatory permitting, and the absence of a mature supplier cluster. A physical building in a new territory remains an inert shell. Matching Taiwan's volume and speed requires transplanting a complete, synchronized operating system of engineers, suppliers, and daily routines. In industrial manufacturing, a true second source is defined as an alternative producer capable of delivering the exact same product design, matching both quality and scale, within a commercially viable timeframe. For advanced silicon, this safety net does not exist. While Samsung and Intel operate advanced semiconductor programs, neither currently provides a viable substitute that combines the necessary production volume, customer integration, and specialized packaging ecosystem. The scale of this dependency is documented in TSMC's 2024 Business Overview, which reports an annual output of approximately 12.5 million 12-inch equivalent wafers. This single network of clean rooms manufactured roughly 11,800 distinct products for 522 independent customers. This output serves as the physical backbone for global computing, powering mobile devices, high-performance computing clusters, artificial intelligence infrastructure, automotive safety systems, and communication networks. Because these advanced chips are designed in tandem with TSMC's unique manufacturing physics, immediately routing production to another foundry is logistically impossible. Customers plan their product pipelines years in advance. A shift in fabrication sources requires complete redesigns and extensive qualification phases. Consequently, any physical interruption within these primary manufacturing clusters, whether triggered by a localized natural disaster, an industrial accident, a utility failure, or a sudden operational shutdown, would not remain isolated to one company's balance sheet. Instead, it would trigger a shared, systemic shortage across unrelated global industries. The crisis would unfold through several distinct operational bottlenecks. Beyond the immediate shortfall of raw wafers, advanced packaging lines would instantly stall, preventing the integration of high-performance chiplets. Downstream equipment manufacturers and consumer brands operate with limited inventory, carrying only a few weeks of safety stock. While these existing stockpiles might temporarily cushion the initial shock, they cannot replace the underlying manufacturing source. Once those physical inventories are exhausted, the absence of a functional second source converts localized operational downtime into prolonged product delays, stalling assembly lines worldwide without a clear path to recovery. This concentration arose without a coordinated conspiracy or a deliberate corporate strategy. It is the logical, emergent outcome of thousands of individual, rational economic choices. Over nearly 4 decades, customers, investors, and suppliers made the most efficient decisions possible, seeking lower costs, higher yields, and faster cycle times. This path dependence reinforced the established manufacturing center, making displacement increasingly difficult. But efficiency and resilience are fundamentally divergent system objectives. The market prioritized the former. While global efforts now focus on geographic diversification, building a new factory in a different territory merely adds nominal capacity. It does not automatically create operational redundancy. True redundancy requires compatible processes, trained personnel, supplier depth, advanced packaging capabilities, and the immense time required for a substitute to take over production. Without these elements, the global semiconductor industry remains an extreme case of critical infrastructure, organized around a highly efficient choke point. The entire system has funneled itself into a corner, operating on a single, irreplaceable structural pillar with no real backup. We have traded redundancy for optimization. Today, the global economy relies on a single, highly concentrated cleanroom network. If that network falters, the silence will be felt in every factory, data center, and device on Earth. The system is optimized to the point of extreme vulnerability.